Now we'll first talk about the deactivating groups. This is part of the previous lecture. Deactivating groups, what they do, they direct the incoming electrophile to the meta position, right? They are also called as the meta-directing groups. You will see something, these meta-directing groups are deactivating groups. They have something in common. You will see that the atom which is directly attached to the benzene nucleus, that atom is either positively charged. The atom which is directly attached to the benzene ring, it is either positively charged or it is positively polarized. It can have any of the two, right? So this is common in deactivating groups or meta-directing groups. They will have an atom which is directly attached to the benzene ring. This atom will be either positively polarized or positively charged. So you can see here you have nitrogen which is positively charged, you have carbon here which is positively polarized, you have nitrogen here which is positively charged, you have carbon here which is positively polarized. So all these groups, they are electron withdrawing with respect to the benzene ring. So this positively charged carbon or nitrogen or any atom or positively polarized atom, it makes these substituents electron withdrawing with respect to the benzene ring. So being electron withdrawing, what they do, they withdraw electrons from the benzene ring and hence they deactivate the ring. They deactivate the ring. So what are deactivating groups? What they do, deactivating groups, will write that deactivating groups will withdraw electrons from the benzene nucleus, from the benzene ring, right? So when they withdraw electrons from the benzene ring, they deactivate this ring. This ring will not be easily attacked by now electrophiles. Electrophile is in search of a electron rich center, but these electron withdrawing groups make this benzene electron deficient. So how come an electrophile will attack this benzene ring? This is the reason why they are deactivating. So you will see, this is the key atom. This is the key atom here. Key atom means which is directly attached to the benzene ring. This nitrogen is the key atom here. This carbon is the key atom here. This carbon here is the key atom. All these groups fall into the category of deactivating groups. Whereas in case of activating groups, what you will see, in case of activating groups, you will see that in case of activating groups, you will see that the key atom, like activating groups, you have NH2, you have OH, right? You have OMe. The key atoms in activating groups, this is the key atom, this oxygen is key atom, this oxygen is key atom. This key atom will have one or more lone pair of electrons. So these lone pair of electrons can, it can form resonance. It can participate in resonance with the benzene ring. As a result, these groups, they donate electrons towards the ring, right? So activating groups, what they do, they donate electrons towards the ring. Deactivating, they withdraw electrons from the ring, whereas these activating groups, what they do, they donate electrons towards the ring. So when they donate electrons towards the ring, what you expect, you will expect that an electrophile can easily attack such a system, right? I'm giving you a table here, a table of these different groups, and this table is very important. You'll see you have a group here. This is the directional effect of the group and relative rate of reaction. Starting with benzene, in benzene, this group will be, obviously it will be hydrogen, right? It will be hydrogen. So it has no directional effect, so no directional effect here. Rate of reaction is 1. So we take it as a standard, right? We take benzene as a standard. We take it to have a rate equal to 1. So with respect to benzene, now we will decide which type of substituents will be activating and which will be deactivating. Means which will have faster rate of reaction and which will have slower rate of reaction. So you have NH2, NHR, NR2. They are ortho para-directing and the rate of reaction is very fast. You have OH group. They are activating groups, right? It's ortho para-directing. The rate of reaction is very fast. OR, activating. This is ortho para-directing. Rate of reaction is very fast, right? In these cases, you will have plus R effect. You will have plus R effect and you have minus I effect, right? And plus R effect will be greater than minus I effect. This is very important here. Then you have alkyl groups and you have halogens. In case of alkyl groups, they are also ortho para-directing, right? So the rate of reaction is fast. And what kind of effect operates in them? The effect is known as hyperconjugation. The effect is known as hyperconjugation. You have halogens. Halogens is a separate class because you will see they have something strangeness to them. Reason being, they are ortho para-directing, but the rate of reaction is slow. This is the only category where you have an ortho para-directing influence, but the overall rate of reaction is slow. So they are deactivating, to be honest, but they direct the incoming electrophile to the ortho and para positions. And in halogens, you will have plus R effect and minus I effect. But in this case, this minus I effect will be greater than plus R effect. The negative inductive effect will be greater than plus R effect. Then you have the COR. This is meta-directing. Rate of reaction obviously slow. These are deactivating groups. These are deactivating groups, and they are activating. They are activating groups, right? So you have SO2OH. This meta-directing rate of reaction is slow. NO2 meta-directing rate of reaction is slow. You have CN meta-directing rate of reaction is slow. You have NR3, this nitrogen positively charged. It is meta-directing rate of reaction is slow, right? So this is demonstration of different groups and their directional effects as well as their relative rate of reaction. So you will in nutshell we will conclude that substituted benzenes that give mainly ortho and para products usually react faster than benzene itself. So you will see that those substituted benzenes which will give ortho and para products, means we are talking about these. In such case, the rate of reaction will be higher than that in benzene. In case of substituted benzenes that give mainly a meta product, in them the rate of reaction will be slower than benzene. Means we are talking about these. The rate of reaction will be slower than in benzene. Now, what is the cause of all this that I have that I have explained so far? Why these groups are some groups are deactivating, some groups are activating? What is the reason behind? So for that purpose, you might have, you might have gone through the rhenium ion mechanism that I have already discussed with you people in the last lecture. In that case, we saw that the first step of the electrophilic substitution reaction is the creation of a carbocation, right? So creation of a carbocation means, the stability of carbocations is decided by, by different groups, right? So if you have an electron donating group, that electron donating group will stabilize the carbocation, and if you have an electron withdrawing group, that group will destabilize the carbocation. So the slow step of an electrophilic aromatic substitution reaction is the addition of electrophile to the nucleophilic aromatic ring to form a carbocation intermediate, that I have already told you. Now, those substituents that are capable of donating electrons into the benzene ring, they will stabilize the carbocation. They will stabilize the carbocation as well as the transition state that leading to its formation. So electron donating group will stabilize both the carbocation as well as the transition state. Therefore, it increases the rate of electrophilic aromatic substitution. On the other hand, if you have substituents that withdraw electrons from the benzene ring, they will destabilize the carbocation intermediate and the transition state, which leading to its formation. Therefore, what they will do, because they will destabilize the carbocation and the transition state, they will decrease the rate of electrophilic substitution reactions, right? First of all, we'll see how these substituents donate or how they withdraw electrons, right? So keep two things in mind. Electron donating substituents, they increase the reactivity of benzene towards electrophilic substitution, whereas electron donating substituent decrease the reactivity of the benzene ring towards electrophilic substitution reactions, right? Three compounds are given here: 1, 2, and 3. Z is it donates electrons towards the ring, so it will be more reactive. Y, it withdraw electrons from the ring, it will be less reactive than benzene, right? Now we'll see how these groups will deal in detail, how these groups, how they donate or withdraw electrons from the benzene ring or towards the benzene ring. There are mainly two methods by which these groups can donate or withdraw electrons. One effect is known as the inductive electron donation, and another is known as inductive electron donation by resonance. So there are two methods. One is through inductive electron donation, and another is through electron donation by resonance. So electron donation can occur through two methods rather. Electron donation, two methods are there. One is known as inductive electron donation. Inductive electron donation. This inductive electron donation is nothing, it is inductive effect. And another is by resonance. Similarly, electron withdrawal. This electron withdrawal can also occur through two methods. One is inductive electron withdrawal. Inductive electron withdrawal, and another is resonance, right? This is minus R effect and this is plus R effect. This is the difference. So first we'll see, so these are the two methods. You must be able, as organic chemists, you must be able to recognize which group will donate or withdraw electrons through inductive effect and which group will donate or withdraw electrons through resonance effect. Similarly, you should be able to understand which group will withdraw electrons through inductive effect and which group will withdraw electrons through a resonance effect, right? First we'll see inductive electron donation and withdrawal through inductive effect. So it is inductive electron donation and withdrawal, means electron donation and withdrawal through inductive effect. For that purpose, you have to keep in mind certain things. If you have a substituent, that is bonded to benzene ring, it is less electron withdrawing than a hydrogen. So hydrogen is used here as a reference. The electrons in the sigma bond that attaches the substituent to the benzene ring will move towards the ring more readily than will those in the sigma bond that attaches the hydrogen to the ring. So you understood this topic, this sentence. If you have a substituent that is bonded to benzene ring, that substituent is less electron withdrawing than benzene, right? So in that case, what you will see that this substituent will donate electrons inductively compared to the hydrogen, because it is less electron withdrawing than hydrogen. So being less electron withdrawing than hydrogen means it can donate electrons towards inductively. It can donate electrons inductively towards the ring, right? So donation of electrons through sigma bond, it's called as the inductive electron donation or inductive effect that you have already studied. You have seen that alkyl groups, CH3 alkyl group, it has plus I effect, so it can donate electrons. So alkyl substituents donate electrons inductively compared with the hydrogen, right? But you must remember one thing here, which is very important, that notice that the electron donating ability of an alkyl group, not the electron donating ability of a carbon atom, is compared with that of hydrogen. It is electron donating ability of a group, not of an atom, is compared, because carbon is more electronegative. Carbon is more electronegative than hydrogen. So from that perspective, this carbon should be electron withdrawing. But we are talking about a group. An alkyl group is electron donor as compared to a hydrogen, right? So it's the electron donating ability of a group, not of an atom. So what do we get here? This CH3 here, this substituent donates electrons inductively, means through inductive effect, compared with the hydrogen, right? So methyl group is an electron donor towards benzene ring. Similarly, this NH3, this substituent withdraws electrons through what effect? Through inductive effect compared with the hydrogen. This nitrogen cannot participate in resonance because there is no lone pair of electrons. So resonance effect is eliminated here. There is no involvement of resonance. Only effect that operates here is the inductive effect. And nitrogen being more electronegative, plus it has a positive charge, so it withdraws strongly electrons from the benzene, right? And this electron withdrawal occurs through inductive effect. So it is known as the inductive withdrawal of electrons from the benzene ring. So if a substituent is more electron withdrawing than hydrogen, like this plus NH3, it's more electron withdrawing than hydrogen, right? It will withdraw electrons away from the sigma electrons. We are talking about sigma electron because we are talking about inductive effect. Sigma electrons away from the benzene ring, more strongly than that of a hydrogen. withdrawal of electrons through this sigma bond, it's known as the inductive electron withdrawal. Yeah, negative inductive effect. We call this as negative inductive effect also. Whereas in case of alkyl group, it is known as the positive inductive effect, plus I effect. Right? The NH3 group is a substituent that withdraws electrons inductively because it is more electronegative than a hydrogen. This is inductive electron withdrawal or donation. Now we'll talk about the second one, which is known as the resonance electron donation and withdrawal.